A rare visitor from deep space is flying through our solar system, and this one is, honestly, mind-blowingly mysterious. 3I Atlas came from beyond our solar system, making it only the third confirmed interstellar object ever discovered. But, new data from NASA and international observatories suggests this ancient traveler might be something far more extraordinary than just another comet racing past the sun. The breaking discovery. On July 1, 2025, astronomers using the NASA-funded Asteroid Terrestrial Impact Last Alert System telescope at Rio Hurtado, Chile, made a breakthrough discovery that would, captivate the global scientific community. They detected a moving object initially designated as A11PL3Z, later confirmed as 3I Atlas, representing the third known visitor from beyond our solar system. This rapid confirmation was achieved through combined efforts of international observers, including the Minor Planet Center and researchers at NASA's Jet Propulsion Laboratory. The object's initial detection proved challenging due to its faintness and location near dense star fields close to the galactic center in the constellation Sagittarius. High-precision astrometric measurements soon revealed its distinctive hyperbolic trajectory and extreme velocity, definitively eliminating the possibility it belonged to our solar system. 3I Atlas's discovery immediately energized astronomers worldwide, sparking an unprecedented campaign of rapid, coordinated observations designed to track this rare interstellar visitor, while maximizing data collection before it became too dim to observe effectively. This extraordinary find underscores the remarkable capabilities of modern telescopic survey systems in uncovering objects once believed completely undetectable, opening new scientific horizons for comprehensive interstellar object research. The discovery story. Between June 25 and 29, 2025, the Atlas survey system, composed of 4 powerful telescopes strategically located in Hawaii, Chile, and South Africa, captured multiple critical detections of the newly discovered object, now officially known as 3I Atlas. The initial observational data appeared as extremely faint streaks against the dense starry backdrop, but gained tremendous scientific significance as coordinated follow-up observations quickly pinpointed its precise celestial path. Simultaneous observations from the Zwicky Transient Facility at Palomar Observatory in California, strongly supported by dedicated researchers like Marco Micheli from the European Space Agency and Daryl Seligman from Michigan State University, helped definitively confirm the object's unbound hyperbolic trajectory, providing compelling evidence supporting its confirmed extrasolar origin. The survey system's remarkable ability to rapidly scan vast areas of sky using advanced wide-field imaging technology proved absolutely critical in detecting this extraordinarily rare interstellar visitor amidst the incredibly dense stellar population near the galactic center, where precise object identification remains notoriously challenging. Extensive archival searches later uncovered valuable pre-discovery observational data dating back to June 14, definitively revealing that this ancient comet had been silently traversing our solar neighborhood for several weeks before achieving formal astronomical recognition and official designation. A stranger in our midst. What makes 3I Atlas truly extraordinary are its unprecedented physical characteristics that, honestly, challenge conventional understanding of interstellar objects. Moving at an absolutely mind-boggling speed of approximately 58 kilometers per second relative to the Sun, this cosmic visitor dramatically outpaces both previous interstellar visitors, Oumuamua and 2I Borisov. Its extreme orbital eccentricity of 6.14 represents the highest value ever recorded for any known celestial object, creating an almost perfectly straight trajectory through our solar system. Initial size estimates suggested the object could measure up to 20 kilometers in diameter, making it potentially the largest interstellar visitor ever observed, though recent Hubble Space Telescope observations indicate a more modest size between 0.32 and 5.6 kilometers. The comet's unusual brightness patterns and early activation, while still 4.5 astronomical units from the Sun, have puzzled researchers worldwide. Unlike typical comets that remain dormant at such distances, 3I Atlas began displaying cometary activity far earlier than theoretical models predict, suggesting either unique composition or potentially artificial characteristics. Its trajectory alignment with the ecliptic plane occurs with only a 0.2% probability by random chance, raising questions about whether this positioning might be deliberate rather than coincidental, adding another layer of mystery to an already enigmatic cosmic visitor. The predecessors. The discovery of 3I Atlas follows two other remarkable interstellar visitors that, really revolutionized our understanding of cosmic wanderers. Oumuamua, discovered in October 2017 by astronomer Robert Warwick at the University of Hawaii, became the first confirmed interstellar object. It measured roughly 400 meters long and had this unusual elongated shape. Its mysterious acceleration patterns sparked intense scientific debate, with some researchers even proposing exotic explanations including possible artificial origins. 2 years later, amateur astronomer Gennady Borisov discovered 2I Borisov in August 2019, which turned out to be a more conventional interstellar comet with typical outgassing behavior and composition. These three visitors demonstrate that interstellar objects may actually be far more common than we previously believed, with improved detection capabilities now revealing a steady stream of cosmic travelers passing through our solar system. The objects display varying characteristics. Oumuamua appeared asteroid-like with no visible coma. Borisov behaved like a typical comet, while 3I Atlas exhibits these hybrid features that just don't fit established categories perfectly. This progression suggests our solar system regularly encounters material ejected from other stellar systems throughout the galaxy, providing, honestly, unprecedented opportunities to study the composition and formation processes of distant planetary systems, without needing to mount expensive interstellar missions to reach them. The cosmic journey. 3I Atlas follows a precisely calculated path through our solar system that brings it tantalizingly close to multiple planets during its brief visit. The comet will reach perihelion on October 30, 2025, approaching within 1.36 astronomical units of the Sun, positioning it between Earth and Mars at its closest solar approach. During its journey, the object will pass remarkably close to several planets: 0.19 AU from Mars on October 3, 0.65 AU from Venus on November 3, and 1.8 AU from Earth on December 19, 2025. These planetary encounters offer honestly unprecedented scientific opportunities to study an interstellar visitor using various spacecraft instruments and ground-based observatories positioned throughout the solar system. The comet's retrograde orbit, inclined 175 degrees relative to the ecliptic plane, means it travels opposite to the planet's orbital motion, adding to its mysterious nature. Computer models tracking its future trajectory indicate 3I Atlas will eventually pass 0.36 AU from Jupiter on March 16, 2026, before departing our solar system forever. This cosmic journey provides a once-in-a-lifetime opportunity for comprehensive multi-wavelength observations, gravitational studies, and potential spacecraft encounters that could, really unlock secrets about the formation and evolution of planetary systems beyond our own solar neighborhood. A scientific goldmine. The arrival of 3I Atlas presents astronomers with an unprecedented scientific opportunity to study pristine interstellar material using cutting-edge technology that just wasn't available during previous visits. NASA's Hubble Space Telescope captured detailed images in July 2025, revealing the comet's coma structure and dust distribution patterns. The James Webb Space Telescope is conducting comprehensive spectroscopic analysis to determine the object's chemical composition, searching for exotic materials or isotopic ratios that differ from solar system objects. Ground-based observatories worldwide, including the Gemini Observatory and Keck Observatory, are monitoring brightness variations and rotational periods that provide insights into the comet's internal structure and density. Advanced computer modeling allows researchers to simulate the comet's behavior under various theoretical scenarios, testing whether observed characteristics match predictions for natural formation versus artificial construction. International collaboration through organizations like the European Southern Observatory ensures continuous monitoring across multiple wavelengths and time zones. The wealth of data being collected right now far exceeds anything obtained from Oumuamua or Borisov, potentially revolutionizing our understanding of interstellar objects, planetary formation processes, and the dynamic environment between stellar systems. This comprehensive scientific investigation may, hopefully, provide definitive answers about 3I Atlas's true nature and origin before it disappears into interstellar space forever. Unanswered questions. Despite intensive international observation campaigns, 3I Atlas continues to pose fundamental questions that challenge our understanding of interstellar objects and their origins. The comet's exact size remains uncertain due to its surrounding coma of reflective dust, which obscures the nucleus and complicates accurate diameter measurements. Early estimates range from 1 to 2 kilometers to potentially 20 kilometers across, representing enormous uncertainty that affects calculations of mass, composition, and internal structure. Dr. John Noonan at Auburn University suggests the nucleus is likely on the smaller end of this range, comparable to 2I Borisov, but definitive measurements await future observations. The object's unusual chemical composition, revealed through spectroscopic analysis, contains isotopic ratios that don't match typical solar system materials, raising questions about the stellar environment where it formed billions of years ago. Its remarkably preserved surface state, despite potentially eons of cosmic ray exposure, challenges models of interstellar weathering and erosion processes. The comet's early activation and controlled outgassing patterns differ significantly from known cometary behavior, suggesting either exotic ice compositions or, possibly, artificial regulation mechanisms. Most puzzling is the statistical improbability of its trajectory alignment and planetary encounter sequence, which some researchers argue exceeds reasonable expectations for random cosmic debris, opening discussions about whether 3I Atlas might represent something more deliberate than natural space debris. The alien question. The possibility that 3I Atlas represents artificial technology rather than natural cosmic debris has sparked intense scientific debate, led prominently by Professor Avi Loeb from Harvard University. Loeb, co-founder of the Galileo project dedicated to searching for extraterrestrial technology, co-authored a controversial paper suggesting the object could potentially represent hostile alien technology based on its unusual trajectory and behavioral patterns. His analysis points to the object's statistically improbable path through our solar system, perfect timing for planetary encounters, and controlled thermal emissions as potential evidence of artificial origins rather than random cosmic wandering. However, the majority of mainstream astronomers strongly reject these claims as premature speculation lacking sufficient evidence, emphasizing that natural explanations remain more plausible for all observed characteristics. Critics argue that entertaining artificial hypotheses without definitive proof undermines scientific credibility and promotes unfounded conspiracy theories about extraterrestrial visitation. The debate highlights fundamental questions about scientific methodology when confronting potentially paradigm-shifting discoveries. Should researchers explore all possible explanations regardless of how extraordinary, or maintain conservative approaches that prioritize conventional interpretations? This controversy reflects broader tensions within the astronomical community about balancing open-minded inquiry with rigorous skepticism when studying objects that challenge established models of natural phenomena and cosmic evolution. Observing the visitor. Astronomers worldwide are employing every available technological resource to study 3I Atlas before it fades from observable range forever. NASA's Hubble Space Telescope continues capturing high-resolution images to monitor changes in the comet's coma and potential tail development as it approaches perihelion. The Swift Observatory is measuring water vapor emissions and ultraviolet signatures that provide insights into the comet's internal ice composition and sublimation processes. Ground-based facilities, including the Very Large Telescope in Chile and Mauna Kea observatories in Hawaii, are conducting continuous photometric monitoring to detect brightness variations, rotational periods, and potential outburst events. Radio telescopes, including the Green Bank Observatory, are searching for any electromagnetic emissions that might indicate artificial communication systems or technological signatures hidden within natural thermal radiation. Advanced spectroscopic instruments are analyzing the comet's chemical fingerprints across multiple wavelengths, comparing isotopic ratios and molecular compositions with known solar system materials and theoretical predictions for interstellar objects. Amateur astronomers using sophisticated backyard telescopes are contributing valuable time series observations that fill gaps between professional facility scheduling. This unprecedented global observational campaign represents the most comprehensive study ever conducted of an interstellar visitor, potentially providing definitive answers about 3I Atlas's true nature and implications for our understanding of cosmic intelligence and planetary system evolution. Dawn of a new era. The discovery of 3I Atlas marks the beginning of a revolutionary era in interstellar object detection and analysis, fundamentally transforming humanity's understanding of our cosmic environment. Dr. James Davenport emphasizes that upcoming facilities like the Vera Rubin Observatory are expected to revolutionize detection capabilities, with projections estimating dozens to hundreds of similar discoveries during its operational decade. This technological advancement will enable comprehensive statistical studies of interstellar object populations, their frequency, composition, and origins, providing unprecedented insights into galactic dynamics and planetary system evolution throughout the Milky Way. The European Space Agency's JWST spectroscopy division continues developing new analytical techniques specifically designed to distinguish between natural and artificial characteristics in future interstellar visitors, preparing for potential discoveries that might challenge fundamental assumptions about cosmic intelligence. Advanced computer modeling and machine learning algorithms are being developed to rapidly process vast amounts of observational data from multiple sources, identifying subtle patterns and anomalies that might escape human analysis. International cooperation frameworks established during the 3I Atlas investigation will serve as templates for coordinated responses to future discoveries, ensuring maximum scientific return from these rare cosmic opportunities. The broader implications extend beyond astronomy, potentially affecting planetary defense strategies, exobiology research, and humanity's philosophical understanding of our place in a universe that may be far more dynamic and populated than previously imagined. As 3I Atlas continues its journey past the Sun, it leaves behind more questions than answers about the true nature of interstellar visitors. Whether this ancient cosmic wanderer represents natural debris from a distant star system, or something far more extraordinary, its discovery has opened new frontiers in astronomical research. The truth about 3I Atlas may reshape our understanding of intelligence in the cosmos. Keep exploring with Simply Science. Like, share, and subscribe for more cosmic revelations. On August 6, 2025, the James Webb Space Telescope slammed into emergency mode to capture an object that, honestly, just shouldn't exist. Astronomers, including the Pan-STARRS team over in Hawaii, expected a dying ball of ice. Instead, Webb's new data on the interstellar comet 3I Atlas just confirmed a chemical nightmare. This visitor isn't just unusual, it's breaking every rule in the book, and the deeper the data goes, the more unthinkable the questions get. Let's explore this together. Emergency override, Webb's unprecedented response. What does it take to stop the world's most powerful space telescope dead in its tracks? On August 6, 2025, we found out. When the alert came from the Pan-STARRS survey, led by principal investigator Ken Chambers, the numbers were, well, alarming. The interstellar object 3I Atlas was accelerating, its spectrum flashing with unexpected metals. There was no time for committees. In a move almost unheard of, a director's discretionary time override was triggered, sidelining Webb's entire multi-million-dollar schedule. This wasn't a normal target of opportunity, this was an emergency. The command chain went straight to the Space Telescope Science Institute director's desk, requiring unanimous approval. It was a massive risk. A single unscheduled slew of that magnitude can cost over 12 hours of precious observation time and risks thermal shock to the delicate mirror segments. This time is meticulously allocated to dozens of other research teams who have waited years for their shot. At 2:17 GMT, after a rapid 38-minute repointing maneuver, the command went live, the tension palpable in the Baltimore control room. Webb's instruments locked onto an object that was already beginning to rewrite cosmic chemistry. Fewer than 4 such overrides have happened in Webb's entire operational history. None for an interstellar object. Early activity beyond Jupiter's orbit. Here's the first red flag that 3I Atlas was no ordinary comet. It woke up in the deep freeze. Most comets are quiet until they cross inside the solar system's frost line near Jupiter's orbit, roughly 5 astronomical units from the Sun. But 3I Atlas was already active at 6.8 AU, far out where the Sun is just too weak to sublimate water ice. Ground-based telescopes, following up on alerts from observers like Karen Meech at the University of Hawaii, noted a persistent brightening of 0.3 magnitudes in just 48 hours. For an object this distant, that represents a massive increase in its gas and dust output. This sustained activity, producing a tenuous coma when the surface temperature was below 150 degrees Celsius, pointed to a body born in a place fundamentally different from our own solar system. Its engine had to be a hyper-volatile ice, something that turns to gas in the slightest warmth of the distant sun. The comet's tail grew at a pace that honestly stunned the teams watching, driven by gases that simply shouldn't have been active so far out. It was the first clue that the chemistry of this visitor, as cometary expert Michael Mumma might put it, was deeply, profoundly wrong. The carbon dioxide anomaly. When Webb's near-infrared spectrograph delivered its first data packet, the anomaly was impossible to miss. The absorption band at 4.26 microns was breathtakingly strong. It's the classic textbook signature for carbon dioxide, and it utterly dominated the spectrum. The final analysis confirmed a carbon dioxide to water ratio of 8:1. That isn't just an anomaly, it's a statistical impossibility based on every comet we have ever studied. For context, even the most carbon dioxide-rich comets in our system barely reach a ratio of 0.3. The gas production rate was staggering, calculated at over 1.5 times 10 to the 28th molecules per second, an output comparable to what the great comet Hale-Bopp produced when it was much closer to the Sun. Every cross-check from Hubble and the Keck Observatory confirmed it. This isn't a calibration error, it's a message, as a planetary scientist like Stephanie Milam at NASA would argue, from a star system where the chemistry of planet formation was completely inverted. Such a system might have formed around a carbon star, creating a world where carbon dioxide, not water, is the dominant ice. Nickel without iron, an impossible chemistry. This is where the story goes from strange to deeply unsettling. As the team at the European Southern Observatory analyzed the high-resolution spectra, they found clear emission lines for atomic nickel at 3,415, 3,524, and 3,525 angstroms. The real shock was what was missing. Iron. In every celestial body ever studied, nickel and iron are chemically inseparable, forged together in the hearts of dying stars and scattered in a cosmic ratio of about 1 part nickel to 15 parts iron. Yet even with the Very Large Telescope's UVES instrument running at a resolving power of 80,000, iron was a ghost. The data was brutal. The upper limit on iron atoms meant nickel outnumbered it by more than 40-1. Spectroscopists like Neil Delarusso at Johns Hopkins would confirm this is unprecedented. The only plausible, though exotic path is the molecule nickel carbonyl, which is so volatile it vaporizes at just 43 degrees Celsius. This molecule is extremely fragile and would break down under solar radiation, releasing the free nickel. But for that to be the explanation, the object had to form in a place that chemically isolates nickel on an industrial scale, a process unknown in nature. Trajectory anomalies and acceleration spikes. As if the chemical puzzle wasn't enough, the way 3I Atlas moved was just as bizarre. Davide Farnochia's team at JPL, who are masters of celestial mechanics, flagged its trajectory before the Webb data even came down. The object wasn't just following the clean arc of gravity. It was accelerating. Over a 72-hour period, its velocity increased by nearly 0.12 meters per second squared, a non-gravitational push far beyond what the observed outgassing could explain. The thrust calculated from the gas production rate was an order of magnitude too low to account for the observed change in speed. The data also showed tiny sharp jumps of up to 1.5 meters per second, as if an internal force was flickering on and off, rather than a steady, continuous jet. This stands in stark contrast to Oumuamua's smooth acceleration. For an 11-kilometer wide body with an estimated mass of over 1 trillion kilograms, this erratic push is like watching a mountain suddenly lurch forward with no visible cause. The physics just doesn't add up. The acceleration was real, and it wasn't coming from ice alone. The lighthouse effect. Mechanical light curves. Every object in space tumbles, but 3I Atlas's light curve is anything but natural. Photometric data from NASA's TESS satellite revealed a periodic brightening that pulsed with the precision of a clock, sweeping like a lighthouse beam every 7.2 hours. A tumbling potato-shaped rock would produce a smooth rolling sine wave of light. This was a square wave, ramping up in brightness by a full 1.8 magnitudes in just under an hour, holding steady, and then dropping off sharply. This implies an object with distinct flat sides and sharp edges, unlike the irregular shapes of natural bodies. Furthermore, outgassing should create torque, causing the object's spin period to change over time. Instead, the 7.2-hour period remained locked in to within 1,000th of a second, a major physical contradiction. An expert on exoplanet light curves like MIT's Sarah Seeger would immediately recognize this as unnatural. The sharp increase in brightness also hints at a highly reflective, possibly metallic surface being periodically revealed to our line of sight. Ancient sky metal. Historical context. You know, the idea of strange metal falling from the sky is actually woven into our oldest histories. Around 3200 BCE, ancient Egyptians hammered beads from iron they couldn't have possibly smelted. These beads, discovered at Giza, are nearly 30% nickel. It's a kind of cosmic fingerprint proving they were made from a meteorite. Centuries later, a dagger was buried with Tutankhamun around 1323 BCE, and its untarnished blade contains 11% nickel. The Egyptians called this material Baya on Pet, or iron from heaven, with a hieroglyph that actually combines sky and metal. Further afield, the Inuit of Greenland used the Cape York meteorite for centuries as a source of iron for tools and harpoons. And as historian Lydia Baum of Heidelberg University notes, these cultures knew this metal was not of the earth. It was seen as a gift, or maybe even a warning, from the gods. This ancient reverence for rare, otherworldly materials really mirrors the intense scientific focus on the anomalous metals being broadcast by 3i Atlas today. Avi Loeb's challenge to consensus. You can't have a conversation about interstellar anomalies without Harvard astrophysicist Avi Loeb. When the data on 3i Atlas came out, he immediately argued in a new preprint that these are all potential hallmarks of something engineered. In the lab, separating nickel from iron is done via the Mon process, which, kind of eerily, uses carbon monoxide to create volatile nickel carbonyl, the exact chemistry hinted at in the comet's coma. Loeb argues that while the community scrambles to invent exotic natural comets, we must apply Occam's razor. Is it simpler to invent new astrophysics, or to consider an existing category of object we've theorized about, technology? His critics rightly say extraordinary claims require extraordinary evidence. But Loeb's position, now supported by his Galileo Project initiative, is that the evidence is already extraordinary. The project's mission is to actively search for technological signatures, and 3i Atlas fits the profile of exactly what they are looking for. Clinging to familiar explanations when the data screams otherwise is a failure of scientific imagination. Scientific community divided. The revelations about 3i Atlas have sent shockwaves through the astronomical community. On one side, scientists like Michelle Bannister of the University of Canterbury are pushing for natural explanations. They propose that 3i Atlas could have formed in a carbon-rich protoplanetary disk around a carbon star, where unique chemical conditions, while improbable, might allow for the formation of nickel carbonyls. It's a theory that pushes the boundaries of known astrophysics but keeps the object within the realm of the natural. On the other side, a growing number of researchers, emboldened by the sheer number of anomalies, are starting to take the artificial origin hypothesis seriously. They argue the combination of its 40-to-1 nickel-to-iron ratio and mechanical light curve is too much to be a coincidence. The debate is raging on preprint servers like ArcSiv, with some suggesting it could be a probe, a solar sail fragment, or even derelict industrial material from another civilization. This isn't an angry argument, but a rigorous process where every theory is being stress-tested against the hard data. NASA's High Anomaly Classification. Officially, NASA's Planetary Defense Coordination Office under Lindley Johnson has flagged 3i Atlas as a high-priority scientific object. While it poses no impact threat, its trajectory is being monitored by JPL's Sentry 2 system with an unusual condition code 9, indicating a trajectory so unpredictable it defies reliable long-term projection. This flag essentially tells the entire astronomical community that all bets are off for where this object will be in the future, making follow-up observations extremely difficult and urgent. Internally, this triggers discussions at the highest levels of NASA's Planetary Science Division about the fundamental nature of the object. It becomes a question not just of tracking, but of understanding. The tension between the cautious public statements and the urgent internal scramble to understand what they are dealing with is palpable. The official line is more data needed, But the unofficial reality is that this object is an enigma of the highest order. So what is 3I Atlas? Is it a cosmic fluke, a messenger from a type of star system we've never imagined, with a chemistry that rewrites the rulebook? Or is it something more? Is this the first truly unambiguous sign that we are not alone in the universe? A piece of technology coasting through our solar system? The data is tantalizing, troubling, and refuses to give us an easy answer. For now, the truth hangs in the balance, waiting for the next round of observations to tip the scales one way or the other. What we do know is that this visitor from the dark has changed the conversation forever. Don't forget to like, subscribe, and hit the bell icon for more deep dives into the mysteries of our universe. What do you think 3I Atlas is? Let us know in the comments below. Thank you for watching Simply Science. 7 visitors from the edge of the void are hurtling towards our sun. While that sounds like the opening of a sci-fi blockbuster, it's actually a snapshot of the constant traffic passing through our cosmic neighborhood. In late 2024 and into 2025, a lineup of comets is set to light up our skies, including one that astronomers are whispering could be the comet of the century. Is this just a spectacular coincidence? Or is our ability to scan the cosmos revealing a sky far more active than we ever imagined? Let's explore this together. The digital sky watchers. Have you ever wondered who finds these cosmic travelers? Every night, a silent network of digital eyes sweeps the heavens. These are the world's automated comet hunters, primarily the Pan-STARRS project in Hawaii and the Atlas survey, a NASA-funded project with telescopes in Hawaii, Chile, and South Africa. Led by principal investigator Dr. Larry Deneau, the Atlas system is designed to scan the entire sky every 24 hours to identify moving objects. Their cameras are incredibly sensitive, able to spot objects down to magnitude 21, which is over 100,000 times fainter than the faintest star you can see with your naked eye. The Pan-STARRS PS-1 camera is a 1.4 gigapixel behemoth, capturing several terabytes of data each night. The real prize isn't a static picture but movement. Sophisticated software compares new images against a vast digital map of the cosmos, flagging any pixel that has shifted. Once a candidate is flagged, an alert is sent to the Minor Planet Center, where Dr. Matthew Holman and his team process the data, triggering follow-up observations from around the globe. They are joined by other powerful surveys like the Zwicky Transient Facility in California, creating a planetary defense network of unprecedented capability. The entire process from initial detection to confirmation can happen in less than an hour. This digital vigilance has completely transformed the field, turning comet discovery from a waiting game into a real-time hunt. 7 against the odds. So, what are the chances of seeing a truly spectacular comet? Astronomers joke that the universe is stingy. The models that predict comet populations, like those from Dr. Harold Levison, show that the confluence of a perfect orbit and a large, active nucleus is incredibly rare. Most great comets are first-time visitors from the Oort cloud, a theoretical sphere of trillions of icy bodies named after Jan Oort, stretching an immense 100,000 astronomical units from our sun. For every comet Hale-Bopp with its 60-kilometer nucleus, there's a comet Kohoutek from 1973. Hyped as the comet of the century, it fizzled dramatically, teaching astronomers a hard lesson about the unpredictability of these icy bodies. As the legendary comet hunter David Levy once noted, comets are like cats. They have tails and they do precisely what they want. Statistical analyses suggest a Hale-Bopp class event occurs perhaps once every few centuries. The odds for a bright naked-eye comet are better, maybe one every 5 to 10 years, but many of those are poorly positioned for viewing. This is what makes the buzz around C/2023A3 so palpable. It's a genuine contender that could defy the odds. The quiet visitors. Not every comet is a headline grabber. Some slip through the solar system as faint smudges, their passage noted only by dedicated observers. Among the 7 visitors of 2025, 2 fall into this quiet category, C/2022E3 or Pan-STARRS, and the periodic comet 240P/NEAT. C/2022E3 reaches its perihelion on July 31st, at a chilly distance of 3.82 astronomical units, or about 571 million kilometers from the Sun. At that range, it's not expected to brighten beyond a modest magnitude 10, visible only in medium-sized telescopes. Then there's 240P/NEAT, which was discovered in 2002 and returns every 7.6 years. It makes its pass on December 19th at a distance of 2.12 astronomical units, or 317 million kilometers. Its performance will likely be even dimmer, a low-key encore for those tracking its well-documented path. For both of these objects, the primary audience will be astronomers contributing data to the Minor Planet Center, where every verified observation helps refine orbital calculations. Even these faint comets provide crucial data on things like nucleus rotation and the slow development of their comas. They are the workhorses of cometary science, providing a baseline of normal activity against which the brighter comets can be compared. The crowd pleasers. Every now and then, a comet arrives that's, well, destined for the spotlight. Back in 2020, it was Comet Neowise, with its 5-kilometer nucleus. But now, all eyes are on C2023 A3 to Tsuchinshan Atlas. Discovered on January 9, 2023, it's on an 80,000-year orbit that will take it to a perihelion of 0.39 astronomical units. Forecast models by Dr. Quanzi Ye suggest it could reach a magnitude of 0 or even brighter, thanks to some powerful forward scattering of sunlight. For a bit of context, another great comet, Hyakutake in 1996, passed a mere 15 million kilometers from Earth, revealing a stunningly long ion tail that stretched over 100 degrees across the sky. Now, while Tsuchinshan Atlas won't pass quite that close to Earth, its intrinsic activity could be very high, with some estimates suggesting a dust production rate of thousands of kilograms per second near the Sun. If it manages to hold together through the intense solar heating, a major uncertainty for any first-time visitor, it could develop a brilliant tail visible even from light-polluted cities, becoming a true generational celestial event that inspires millions to look up. Spacecraft Symphony. So, what happens when a comet is hiding in the sun's glare? Well, some of the 2025 visitors, like 414P Stereo, will be almost impossible for us to see, but they'll be front and center for a fleet of solar spacecraft. On September 27th, 414P reached perihelion at just 0.504 astronomical units, or about 75 million kilometers from the Sun. From our perspective, it'll be lost in the bright sunlight. This is where missions like SOHO and Stereo and experts like Dr. Carl Badams of the Naval Research Laboratory come in. Their coronagraphs, like SOHO's LASCO instrument, are designed to block the sun's direct light to monitor solar storms, which gives them a perfect view of sun-grazing comets. These instruments can reveal details about their activity that ground-based observers, well, just completely miss. In addition to images, spacecraft like the Parker Solar Probe and Solar Orbiter could use their plasma detectors to directly sample the material in a comet's tail if their orbits happen to align. This would provide an in-situ measurement of the tail's composition and its interaction with the solar wind, which travels at speeds over 400 kilometers per second. These missions really offer a completely different perspective, turning the entire inner solar system into a coordinated laboratory. The 6-month marathon. The arrival of a great comet isn't just a single night's event, it's really more of a marathon. For C2023 A3, the show unfolds over months. For most of early 2024 it was a faint target, brightening from magnitude plus 12 to plus 10. But the real action begins around its September 27, 2024 perihelion, the so-called danger zone where tidal forces and thermal stress are at their peak. Its closest approach to Earth comes around October 12, 2024, at a distance of about 71 million kilometers. Throughout this journey, thousands of observations from amateurs provide a continuous light curve, basically a plot of its brightness over time. This data, often compiled by organizations like the Association of Lunar and Planetary Observers, or ALPO, is crucial for spotting sudden outbursts or signs of fading. Citizen scientists like Terry Lovejoy, who has discovered 6 comets, play a vital role in this global effort. The compressed schedule really turns the sky into a living laboratory, a story that unfolds night after night, with data from around the world painting a complete picture of the comet's behavior. Tales of two tails. So, why do comets have tails, and why do they sometimes have two? The answer goes back to the 1950s when German astrophysicist Ludwig Biermann first proposed the existence of a continuous solar wind. And well, he was right. Every comet grows at least one tail, and often two as it nears the sun. The dust tail is broad, curved, and pale, made up of silicate and carbonaceous dust grains that are pushed away by sunlight. This tail can stretch for over 10 million kilometers, with its particles moving at a relatively leisurely pace of a few hundred meters per second. The ion tail, on the other hand, is a straight, narrow blade of electric blue, formed when the solar wind ionizes gas molecules like carbon monoxide. The solar wind then grabs these ions and hurls them away from the sun at hundreds of kilometers per second, creating a tail that can exceed 100 million kilometers in length. The blue color comes from fluorescence, mainly from ionized carbon monoxide or CO+. And, if the geometry is just right, observers on Earth might even spot an anti-tail, where dust in the comet's orbital plane appears to point toward the sun. These two distinct tails offer a direct, large-scale visualization of the invisible forces shaping our solar system. When solar storms strike. A comet's tail isn't just a passive trail, it's actually a battleground. The sun sometimes unleashes a coronal mass ejection, or CME, which is, well, a billion-ton cloud of plasma. On April 20, 2007, Stereo A watched a CME slam into comet Encke. As analyzed by heliophysicists like Dr. Angelos Vourlides, the footage showed the comet's ion tail being sliced clean off by magnetic reconnection. This happens when the CME's magnetic field lines snap and explosively reconnect, releasing immense energy. A fast CME can travel from the sun to Earth's orbit in as little as 15 hours, moving at over 2,000 kilometers per second. And you know, this isn't rare. Comet C2011L4, or Pan-STARRS, also experienced a dramatic disconnection in 2013. These events provide a unique, large-scale plasma laboratory, allowing scientists to witness physics impossible to replicate on Earth. Seeing a tail disconnect is a visual proxy for a plasma cloud that could later impact our planet, providing a beautiful, if a bit ominous, early warning of potential geomagnetic storms. The Interstellar Outlier. So what happens when a visitor from another star system drops by? Nothing in the 2025 lineup is as scientifically valuable as 3I Atlas. It follows in the footsteps of 1I Oumuamua and 2I Borisov, which gave scientists like Dr. Karen Meech our very first chance to study material from other star systems. Early observations of 3I Atlas from the James Webb Space Telescope are already, honestly, staggering. The coma, its glowing envelope of gas and dust, has been measured at nearly 700,000 kilometers across, half the diameter of the sun. The nucleus is ejecting fine dust at a rate of 6 kilograms per second. What's truly shocking is its chemistry. Spectroscopic analysis reveals an 8-to-1 ratio of carbon dioxide to water, a composition unheard of in solar system comets. This implies 3I Atlas formed in a region of its home star system that was far colder than our own Kuiper belt, below the CO2 frost line. The most tantalizing possibility, however, is that simulations show its dust trail may cross Earth's orbit in mid-2026. This could create the first-ever meteor shower of interstellar material, allowing us to capture and analyze dust from another star as it burns up in our atmosphere. Windows to wonder. So, how can you see the next great comet for yourself? For C2023, A3 Tsuchinshan Atlas, the key dates are in late 2024. The best viewing window is predicted to be from roughly October 12th to the 20th. It will appear in the evening sky, visible in the west about 60 to 90 minutes after sunset. Use an app like Stellarium to pinpoint its location as it moves from Virgo towards Serpens Caput. Give your eyes at least 15 minutes to adjust, and try using averted vision. That means looking slightly to the side of the comet. This uses the more light-sensitive rod cells in your peripheral vision, making faint objects appear brighter. For those wanting to take a picture, a DSLR camera on a tripod is really all you need. Using a standard lens, try an exposure of 10 to 15 seconds at an ISO of 1600 or 3200 to capture both the comet and the background stars. As veteran observer Johnny Bortle would advise, brightness predictions are notoriously difficult. The goal is to go out and look, regardless of the final outcome, to witness a rare and beautiful cosmic event. The Great Comet Parade of 2025 is more than just a rare celestial alignment. It's a profound reminder of the dynamic, ever-changing universe we inhabit. From quiet, distant travelers to brilliant crowd-pleasers, and even a visitor from another star system, this event offers something for everyone. It's an unprecedented opportunity for scientists to study these icy relics in real time, and for all of us to connect with the cosmos on a personal level. So, get your binoculars ready, mark your calendars, and prepare to be amazed. This is a sky show you won't want to miss. Don't forget to like, subscribe, and hit the bell icon for more updates on this cosmic event. Thank you for watching Simply Science.